Okay, this is Professor Thompson. I'm going to go back to 4.4 and do another sketching problem, and this is 29, which is x tan x. And it's only from minus pi over 2 to pi over 2 as part of the problem. So that's right at the edge of where tangent has asymptotes. And so in that region, the domain is everything because tangent's defined in its period, and then x is defined everywhere, so that's fine. That's how I got A. And then the x and y intercepts. If x is 0, then so is tan 0, and you get 0. Tangent is 0 infinitely often, but only once each period, right at the middle of the period. So because we're only looking at one period, you don't get any more points where y is 0. So that's our only intercept. Now there's no limit, there's no asymptotes directly within our domain, but we should look at the edge because we're still approaching pi over 2. And the limit there for tangent is infinity, so it's pi over 2 times infinity, which is infinity. And the limit as x goes to minus pi over 2, you get minus pi over 2 times minus infinity. So because of the sign of x, you get infinity again. So tangent normally goes down on the left and up on the right, but this is going to go up on both sides. So it's good for us to check that. And so those are our two vertical asymptotes. We can't worry about horizontal asymptotes because we're not actually going to infinity on either side. So those are limits at infinity, but we're not going there in our domain. So excuse me, that was part D. I jumped ahead. So let's go back and do C. C is symmetry. So it's not periodic because of the x, but if we plug in minus x, tangent is an odd function, so I can pull the negative out. So that becomes positive x tan x, or just x tan x, because the two negatives cancel. So what that tells me is that this is actually even, which is kind of surprising. And so that makes sense why that it's going to infinity on both sides, because it's an even function, so it's going to look symmetric around 0, 0, around the y-axis. Okay, so now we're ready to do our sign chart and all that. So let's go to E. So I need to take the derivative, which is, I'm going to use the product rule, so I get tan x plus x secant squared x. And so I need to know where that's undefined, but it's not undefined from minus pi over 2 to pi over 2. All in that region is defined. So I just need to set it equal to 0. And to do that, let's write this as sine x over cosine x plus x over cosine x squared. So I can multiply the top by the sine by cosine. So I have sine x cosine x plus x, and then I get cosine squared x on the bottom. So we already know cosine is not 0 until I get out of my regions. So I care about when is sine x cosine x plus x equals 0. I'm not really sure what the book wants you to do here. I wouldn't give you something unsolvable, quote unquote, like this on your test, but I'll just go ahead and finish the problem here. X is 0 is the only answer. And one way to think about it is if you write minus x equals sine x cosine x, you're trying to figure out when those agree. And this is 1/2 sine 2x using a trig identity. So if you're looking at a graph of sine, essentially, the graph of minus x, the only place where they hit is 0. So that's one way to think about it, but there's no algebraic way to solve this that I can think of off the top of my head. So anyway, we get 0, so our sign chart just goes from minus pi over 2 to 0, and 0 to pi over 2. And we do want everything factored, so I guess we have just x plus sine x cosine x on the top and cosine squared x on the bottom. So I multiply those signs, and that'll tell me if f is increasing or decreasing. So if I use, say, minus pi over 4, then x is negative, right, minus pi over 4, and then in that region, cosine is positive, but sine is negative, so I subtract, and they're both square root of 2 over 2, so I subtract 1, so it's negative. This is always positive, so it's decreasing. Now if I use pi over 4, that's minus pi over 4 plus 1. Pi over 4 is basically 3.14 divided by 4, so it's less than 1. When I add 1, I get positive, positive, increasing. So I do get a local min at 0, 0. Now, the y value is 0 because that was what happened with the original function, not because that's what happened with the derivative. So you always plug the x value back into the function. So this is x and this is y of x. Okay, so now we want to take our second derivative. So I'm going to go back to how I had defined our derivative before. When I first did it, it was tan x plus x secant squared x. So now the second derivative is going to be secant squared x plus secant squared x, so now I got to use the product rule, plus x times 2 secant x secant tan x. So if I factor secant squared x out of everything, I get 2 plus 2x tan x. Alright, well, secant squared x we already said was never 0 in this region or undefined. Neither is tangent. So it's not undefined, excuse me. So I want to just check when this guy is 0. So if I divide by 2, I've got 1 plus x tan x. So I want to know when x tan x is minus 1. And this one, even though it's not solvable, this one we can reason through, because at the beginning we said that x tan x was even, and we said that 0 is a local min. So our graph, we know, is going to look like this. We're just trying to figure out which kind of concavity, but it stops right at the axis. So in this region, x tan x is never negative. It's always 0 or less, so there's no solution. So that means we don't get any critical values in this region. So you just need to look at the whole region and check the concavity. So our second derivative has two factors here. So let me write them on the next slide. So it was secant squared x, and then 2 plus 2x tan x. And so let's just check the concavity at 0. So we're looking at this interval, so let's use the test interval 0. This will tell me if f is concave up or concave down. So if I plug in 0, I get 1 and then 2. So that's positive, so it's positive, so it's concave up. Alright, so this is not a very exciting graph. What we found was that it's always concave up, and it's got a local min right at 0. But it does have asymptotes at pi over 2 and minus pi over 2. And it approaches infinity on both sides. So basically this kind of looks like one of the pieces of either secant or cosecant, where it makes that smiley shape and then frowns and smiles. So that's your final graph here, and then the point here is 0, 0. And our asymptotes are at pi over 2 and minus pi over 2. Alright.